All right, this is Rust and Zig together. I'm Richard Feldman. So I've been working on this programming language for several years called Rock. This is not a talk about Rock, but it sets the stage because something I didn't know about GitHub is that GitHub actually has analytics for your pages. And I found this out because we had a list of analytics for our repository visitors, and one day we got a big spike out of nowhere, and somebody told me about this, and I was like, first of all, I didn't know GitHub had analytics, but now that I do know, why is this happening? Where is this coming from? And it turned out that somebody had written a blog post that went viral, and it linked to one of our FAQ entries, which is, why does Rock use both Rust and Zig? And apparently, a lot of people had questions about this. So how many people here are familiar with both Rust and Zig? Okay, so some, but less than half. So one thing that these languages both have in common is that they're very fast. They're good for like high performance. You want to build a program that runs really fast. Either one of these languages is a good choice for that. But they have quite a few differences. So Rust is a very complex language. Its sort of marquee language feature is the borrow checker. You may have heard of this. It's basically a way to help Rust programs have more guarantees, especially around memory safety and certain things around concurrency. And it's both a source of big learning curve, but also a source of a lot of the benefits of the language. Now Zig, by contrast, is a very simple language, which appeals to me. It has a sort of marquee feature called comp time, which is basically where you can write Zig code and have it actually execute at compile time rather than at runtime. So it lets you like pre-compute a lot of things. Really nice feature in a high-performance language, and it's really simple and doesn't have as much of a learning curve as like a macro system or a distinction between like const and non-const functions. And also Zig has a really nice tool chain. I'm going to talk a little bit more about this later. But for example, you can do things like, I want to build my Zig program and I'm on a Mac, but I want to build an executable that runs on Windows or one that runs on Linux. And maybe I'm on an ARM Mac, but I want it to run on an Intel machine. You can do all that sort of out the box with Zig. It's really, really good at those things. Now the question is, why would you actually use these two things together? It seems like they're both different ways to approach the same thing, and this is exactly why so many people were coming to our FAQ entry, is people were wondering the same thing. And I saw in a lot of the discussions about, on this blog post and others, around like comparing Rust and Zig, a lot of things that I thought, oh yeah, that's right, and a lot of things like, that's kind of missing some nuance or kind of missing the picture. And I sort of realized that there's an interesting question here, which is why do we do this, and why might somebody else want to do this? But also along the way, there's a lot of interesting questions around memory safety and things that I think deserve some more nuanced discussion than what I've been seeing around these things. So let's talk about these things. We're going to start by just talking about answering the question, like why did we mix Rust and Zig in the first place? Then I'm going to talk a little bit about memory safety in practice and some of the nuance that I think is missing from some of these discussions. And then finally conclude with like where to draw the line. If you're going to be mixing these two things, where would you want to decide to like draw that line? Okay. So I have to start by telling a little bit of a story. This is called the storekeeper bug. So back in the day when I got into programming, I started off with BASIC, and then I moved on to Visual Basic, and I started making games in Visual Basic. This is like around middle school era, 1990s. And so at some point, somebody told me, if you're going to make games, what all the professionals use is C++. And I, not really knowing what C++ was like, well, that's what I'm going to use. And then someone was like, well, if you're going to learn C++, you should really learn C along the way. So I was like, cool, then I'm going to learn C. So I did. I went and learned C and then kind of learned C++, but honestly, the way I was using C++ was mainly just like using the C++ compiler in kind of a C style. So I wrote this role-playing game in quote-unquote C++, but really kind of C. And at some point, I was walking into town, as I had done many times before in the game, and the storekeeper greeted me with, as he always did, hello, traveler, the text being displayed across the screen. And then one time, I walked into the store, and instead of saying hello, traveler, he said, hello, traveler, and a bunch of memory garbage appeared on the screen. And I was like, what do I do about this? I know I didn't write that string anywhere in my program. What's happening here? This is just a very scary bug to encounter, especially for a middle schooler. And I really was sort of at a loss to like how I could possibly debug this thing. To this day, I don't remember exactly how I did eventually fix the bug, but as I recall, it was something along the lines of, I gave up on how to fix the bug proper. I just went around refactoring other things and cleaning them up, and eventually one of those somehow fixed it. But this is an example of a memory safety bug. And yeah, these are like really scary things. And so when I got into industry, I sort of gravitated towards like automatic memory managed language, garbage collection and stuff like that, in part because I didn't want to have to ever deal with that sort of thing ever again. So fast forward a couple decades, and I'm creating this language called Rock. And again, not really talk about Rock, but this is an automatic memory managed language, so it doesn't have that sort of category of problems, at least in the language itself. And this came up for me, this like Rust and Zig question, because Rock's tagline is it's a fast, friendly, functional language. And that fast part applies not just to Rock programs should run fast, but also the Rock compiler itself should run fast. So if we're building a fast compiler, which is the goal here, I really didn't want to get stuck with like a sort of performance ceiling. Like sometimes something that can happen is you choose a particular language for a task, like building a compiler. You get partway through and you realize, I can't squeeze any more performance out of this language because there's a garbage collector. There's something in my way that I just can't push through to make it any faster. The only way to get it to go faster is to rewrite in a language that has a higher performance ceiling. So I didn't want any performance ceiling here. I didn't want to hit one. I wanted to say, look, I'm going to start from the get-go making this compiler in a language that has the maximum performance ceiling I can get. But at the same time, I also didn't want to worry about these like memory unsafety bugs, this storekeeper, hello traveler, memory garbage stuff. I didn't want to have that experience because I still remembered it from middle school. So knowing that I wanted maximum performance and also didn't want to hit memory unsafety bugs, Rust was sort of this obvious choice. Now, I'd heard that Rust was a language that lets you write code that runs really fast, and part of the reason for that is that it has no garbage collector, unlike other languages that I was familiar with. Also, I'd heard that it was sort of like good with concurrency, and kind of these were like the sum of my knowledge of like why Rust was considered fast was like, I don't know, it doesn't have a garbage collector and it's good at concurrency. Little did I know this was like the tip of the iceberg, and like I had no idea about arena allocation or CPU memory caches or branch misprediction or SIMD instructions or this long list of things that I did not know at the time. But nevertheless, this was sort of what led me to pick Rust as the I wrote the first lines of the Rock compiler in January 2019. This was the reason. So how did it go? Well, if you're not familiar with Rust, but you are familiar with Haskell, this reminded me a lot of learning Haskell. So in one way, because there was this brain-exploding learning curve. There were all these concepts that I ran into where I'm like, I know like more than a dozen programming languages. I've never encountered anything that resembles a borrow checker or lifetime annotations or stuff like this. This was all like brand new stuff that I'd never seen anywhere and never seen anything like it anywhere. And I remember the same kind of feeling when I encountered some things when I was learning Haskell. In terms of language complexity, there's just a lot there. I mean, separate from the fact that there's a lot of new concepts to learn, there's also just a lot of concepts, period. There's just it's a big language. But at the end of the day, also like Haskell, once I did actually get my code working, I had a lot of confidence. So I was like, okay, this is not going to break. This is not going to give me the storekeeper bug. And also, I just even compared to other like garbage collected languages I'd use, I felt like a lot of confidence in refactoring kind of reminded me of Elm in that way, like in a positive way. So this confidence was really kind of the thing that made me say, okay, cool, the learning curve, the language complexity are worth it. I'm happy with this choice. Like I'm glad that I chose Rust for this compiler. This is something I want to keep building on. Now there's this one particular use case inside of our compiler called built-ins. So built-ins are basically language primitives. So these are things like numbers, strings, lists, things that are like baked into the language, and they're partly implemented in Rock. So like we'll have a function called like do this thing with a string, and some of it will be Rock code. But then partly, once you get to a certain point, there's this sort of like irreducible. We just need some sort of lower level primitive thing that really shouldn't be exposed in user space because it's unsafe or something like that. So it's partly that these are implemented in Rock, and then partly there are sort of these primitives that are built into the compiler itself, hence the term built-in. So at first, when we were building these built-ins, we implemented them with manual LLVM calls. How many people know what LLVM is? Okay, so a mix. So for those that don't, LLVM is basically a way that you can, as a compiler author, take your code and translate it into machine code while having some optimizations done on it. So you basically call these functions in LLVM that say like, hey, I want a conditional here, or I want you to make an add instruction, or something like that. And LLVM will say, okay, cool, I can turn that into x86 code or ARM code or Linux, Mac, Windows, whatever. And along the way, it can do a whole bunch of optimizations on it. It's really good at optimizations. So unfortunately, writing manual LLVM calls is kind of like writing assembly language, but with much more ceremony. So it's like you get all of the really low-level fiddliness of assembly, but instead of the conciseness of assembly, you get like all the ceremony of, I don't know, it's like one of the most, so let me just show you an example. So let's say I wrote this Rust code that says if length 1 double equals length 2, then we'll do something in the then block, else do something in the else block. Really straightforward, simple code. Just have a little conditional comparing two numbers together, and then we have a then and we have an else. So here's the equivalent in manual LLVM calls. This is also Rust code. This is the Rust code that generates the LLVM calls. So this is actually something I took out of the Rock compiler. So we have let then block equals context.append basic block, parent then, else block equals context.append basic block. You can kind of see where the verbosity and the ceremony is coming up here. env.builder.build conditional branch. This is our if. Build int compare. So we have to say, okay, we're going to compare these two for equality. Int predicate eq, len1, len2, and then double equals. And we have the then block and the else block, and then later on these are both going to get mutated with the contents of whatever goes in here. So that was if then else in manual LLVM calls. What if we wanted to do something slightly more complicated, like comparing two arrays, where you're going to compare each element in the array to see if they're equals? Well, this is a little bit longer than what we saw the if then else. So it's this, also this, and then also this. That's what array 1 double equals array 2 looks like in manual LLVM calls. So now imagine this, and you're like, cool, now let's build a hash map in manual LLVM calls. No, thank you. So once we got to a certain level of like complexity in our built-ins, we're like, okay, we want to get higher level with this. We don't want to keep like writing this really low-level manual stuff with all this ceremony. This is getting really painful and also difficult to maintain. How can we get something a little bit higher level going for our built-ins? So fortunately, some languages can compile to LLVM bitcode. And basically what that lets us do is it's something where we can load this .bc file off the disk and then mix it in with our Rock compiler output, which is sort of dynamically generating LLVM stuff. And then putting those two together, we can sort of emit the same stuff as if we'd handwritten it. So languages that can do this include C, C++, Zig, and Rust. And basically, this would mean that we could actually like literally write this Rust code in our built-ins instead of all of the expanded version that we were previously writing by hand. So obvious first choice for this is like, well, let's use Rust because we're already using Rust for the compiler. Why would we want to introduce a new language if we didn't have to? Let's just use Rust as our higher level language for the built-ins. So we pretty quickly discovered that we needed this unsafe keyword all over the place. So in Rust, they have a special keyword for when you need to do something that's memory unsafe and sort of step outside some of Rust's guarantees. And this was necessary all over the place, in part because basically we're generating this arbitrary LLVM code. That stuff can just do basically machine code stuff. It's completely unsafe, 100%. And the whole point of this is we were generating stuff that was going to interface with this arbitrarily unsafe stuff, and Rust correctly says, hey, this is unsafe, you need the unsafe keyword, and that was just all over the place with these things. So that was both annoying and also meant we're not really getting a lot of Rust's guarantees, which is like one of Rust's big selling points. It actually turned something that was normally a selling point into kind of like an annoying downside. Also, in some cases, when you use the unsafe keyword with Rust, there's this tool called Miri, which can help you out, like discovering certain potential sources of problems. But unfortunately, foreign function interfaces, namely when you're sort of combining your Rust code with another language, which is what we were doing here, you're just kind of on your own to sort of figure out how to navigate that. You don't get help from Miri on that. Also, I don't remember exactly what the problems were, but Rust-generated LLVM was causing some problems at the time. I talked to some other people who remember like this era when we were making this decision, and they couldn't remember either. But suffice it to say, like there were also some concrete, like we tried to do it despite these problems and ran into other problems with the actual implementation, including some basic tooling and development build difficulties. Where I also kind of vaguely remember there was like a WebAssembly specific thing. If you want to see how we're using WebAssembly in Rock, by the way, check out Brian Carroll's talk from day one. It's really cool. And he showed like an online REPL that we built in Rock. But basically, putting all these things together, we were like, okay, the obvious first choice of Rust is not working out well for this use case. It's working out great for the compiler, but not for this, not for the built-ins. So the next question that we asked was, hey, why not C? Why don't we just try a different language that's a lot less verbose than handwriting this LLVM, and maybe it'll go better for various reasons. Well, of course, this leads me back to I remember what it was like when I was doing some C, and I had a lot of bad experiences with this. But because I'd spent so much time with Rust at this point, when I went back and revisited sort of my past experiences with C and C++, I felt a lot more well-equipped to understand these types of things. So I actually want to go through this bug real quick, and this code is sort of lost to time. I don't know exactly like what the bug was, but I have like a guess as to what it could have been, like an example of that. And this is, I think, actually an interesting way to illustrate like some memory safety in practice. So let's just talk through this real quick. All right, so remember that what it's supposed to say is hello traveler, but instead what it says is all this gibberish around it. So let's kind of zoom in on the hello traveler part of this. So in memory, like the actual bytes that are happening here would be these. So these are ASCII bytes. Back then it would have been literally ASCII. Today, most likely you would see these same bytes because it's UTF-8, which happens to have the same the same numbers in memory for these particular set of characters as ASCII would have. But basically, this is just like these are the numbers that are associated with the particular characters. Now, let's suppose that this was in a C style called a null terminated string, and this would have been literally what I was using at the time. So this is where basically you have a little 0 on the end of the string, a 0 byte, that marks the end of the string. So in some languages, this will be stored separately, like you'll say, here's the string, and then I'll have a number, which is here's the length of the string. But in C, and also in some cases in C++, this is a really common way to do it too, is you had this 0 at the end of the string that marked the end of the string, and then you didn't store the length. You just said that's just a part of the string itself. So now let's imagine that I had some algorithm where I wanted to change the greeting from hello traveler with a dot to hello traveler with an exclamation point if the shopkeeper was really happy to see you because you're a return customer or something like that. So this would be almost exactly the same bytes. The only difference would be the dot byte would be 46, and then the exclamation point would be 33. And if I were writing some C code that wanted to change the last byte of the string from a dot to an exclamation point, I might write it like this. So string, square bracket, str length -1. Let's assume we'd already calculated the string length ahead of time. And str square bracket something is, if I set it equal to this, in C, it's going to just basically write a new byte there. And the exclamation point is going to be 33. So you can imagine that I might have literally written this code if I had been doing this translation between the period and the exclamation point. You might also imagine that a bug or a mistake I might have made would be a classic computer science one, the off by one error. So let's suppose that instead of writing the correct code, I forgot the -1 there. That's certainly something I did a lot when I was newer to programming. And now I've gotten burned by it so many times that I don't do it as often, but I can't say it's 0. But let's say that I wrote this code. And now the 33, rather than being written here, ends up being written here. So there are two consequences here. One is that we still have the 46 for the period here because I didn't write to that location. And the other is that I overwrote the 0, which means we no longer have a 0 marking the end of the string at all. So where is the end of the string? Well, it's wherever we happen to encounter a 0 in memory next. Whatever it happens to be in between that, who knows? Maybe it looks like this. So this is actually a plausible explanation for how I could have gotten this bug, is I wrote over the 0 that was terminating this string, and I could have done that maybe in this logic or maybe completely somewhere else in the program. But the point is that I had probably an off by one error somewhere, I overwrote the 0, and then all of this gibberish was just other stuff that happened to be in memory at that location getting printed out because C thought the string didn't end until it finally, by sheer coincidence, happened to hit a 0 byte after all of this gibberish. Now this stuff might have been strings, it might have been numbers, it might have, it's just ones and zeros in memory, and C's just choosing to interpret them as ASCII because it, doesn't know any better. But keep in mind that this is not, if it's just a game, it's kind of funny when you have a bug like this, but this could have been like a secret. This could have been a password in that memory. There could have been all sorts of sensitive information in those bytes that's now just getting printed out to the screen in plain text. And also it might have been that, instead of this being a middle schooler's game, this could have been like a production server, and maybe instead of printing it out to the screen, it was sending it over the network or writing it to a database or something. There's all sorts of really bad stuff that could have happened here that was much more serious than my silly little bug. So this is one of the reasons that people call this memory safety. This is a memory safety bug right here, and it's an example of memory unsafety and one of the bad things that can happen when you have memory unsafety. So this particular line was the bug where I wrote str bracket str length equals exclamation point. And different languages handle this in different ways. So we saw that in C, what basically it'll do is it'll just silently overwrite whatever is there. At whatever that str length byte is, it's just going to overwrite it. And it's the same thing in C++ because C++, one of the early selling points of it was backwards compatibility with C. So they made square brackets work the same way as they do in C. So you could sort of copy paste your C code over and have it, in a lot of cases, just work. Now Rust, an example of Rust's improved memory safety compared to C and C++ is that if you write the same syntax in Rust, what you're going to get is an error index out of bounds, like you would in a lot of automatic memory managed languages. So this is because in Rust, what we have here in this str, it's represented differently. In C and C++, this is just a memory address, but in Rust, it's a memory address of the start of the string and also a length. So Rust actually knows what the length of the string is, and so it can check at runtime and say, hey, I noticed that this length is bigger than the length that you gave me, or equal to it in this case. This is not going to work. This is going to cause memory unsafety, so instead of doing that, I'm going to give you an error at runtime. This is also what Zig does. So Zig also has square brackets, and Zig has a data structure they call a slice, and what it does is, depending on your compiler settings, is it will give you an error index out of bounds, just like Rust would. So this is an example of how both Rust and Zig are addressing a really common memory safety problem known as a buffer overrun. And you might think, oh, well, how often does this actually come up? You made that mistake in middle school. Turns out this is actually a big deal. Like this type of error, this memory unsafety error, comes up all the time in practice. So this is a Microsoft report from a few years ago. They looked at critical vulnerabilities reported from like 2006 to 2018 across a whole bunch of different code bases. They found that 70% of these critical vulnerabilities were due to memory unsafety in C or C++. Some of these CVEs are buffer overruns, just like what we saw a second ago. A buffer overrun being where you accessed memory outside the range of like an array or a string or something like that that you weren't supposed to access. Now, bounds checks, like what we saw that Zig and Rust are doing, those prevent buffer overrun vulnerabilities, but these are not the only types of memory unsafety. So unfortunately, Microsoft didn't break down what percentage of those the critical vulnerabilities were memory unsafety due to buffer overruns versus other, but let's just briefly talk about two of the other types of memory unsafety. Kind of is like a big three, and these are the other two. So here's another really common line of code that I would have written all the time in C. Array equals malloc 321. Don't need to worry about exactly what this is doing, but basically malloc is short for memory allocate. And when you want to make an array and you don't know what size you want at compile time, which is really common, usually you don't know what size you want until you're actually running the program, you pass in some argument to malloc saying, hey, here's how many elements I want in this array or how many bytes I want. And then malloc says, cool, I will allocate that much memory for you, and then I'll give you back the address of that memory, and that's what's actually the array is going to store. So then I do a bunch of stuff in my program, and then later on I have to call this function called free, and passing in the array, which is the address of that memory, which will basically say, hey, I'm done with this stuff now. You can deallocate this and give it back and reuse that memory later. Now this is important because if I don't do the free, then I'm going to have a memory leak. Basically, I'm going to allocate this memory, and since C does not have a garbage collector, it's just going to stay in memory forever. And maybe sometimes that's what you want. There are certain categories of programs where that makes sense. If you have just a script that kind of runs from start to finish, maybe you don't want to bother deallocating it. That's fine. But most programs do, at some point in their execution, want to actually free something, at which point you've introduced the possibility of a use after free bug. So this is where you call free on the array, and then later on, you forget that you've called free earlier, or maybe there was like a conditional branch where sometimes you called free and sometimes you didn't, and you didn't realize that there was a certain set of circumstances in which you might actually be using this thing after you'd called free on it. And the problem with that is, as soon as you call free on it, that means if somebody else calls malloc somewhere else in your program, so you might say, oh, cool, that memory is free, I'll just go ahead and give you that, and now you have two different variables that are now referring to the same thing, and you had no idea. All sorts of terrible, terrible things can happen as a result of this. So this is also considered a memory safety bug, a use after free. Now there's a variation of that where you call free on something, you do a bunch of other things, then you call free on it again. This is called a double free bug, and it ends up having basically the same kind of symptoms as a use after free. And the reason for this is basically if I call free and then I forget that I called free on it again, what can happen is that second time when I free this memory, maybe somebody else was assigned that same address because I called malloc again and said, oh, this memory is free, I'll assign you that address, and now I have freed something that was already in use, is still in use by some other variable. So it ends up being sort of the same symptoms as a use after free. So again, you don't need to know this in super depth. The point is that use after free and double free are kind of the other two major types of memory safety that people encounter aside from buffer overruns. Okay. Now Zig does have something to help make, reduce the odds of this happening, and it's called the defer keyword. And basically what this does is it's a way to say, I'm going to write my free immediately after my malloc on the very second line, but of course I don't want it to run yet. And so what defer does is it says, cool, you can do whatever the program wants to do in the rest of this function. I'm not going to actually call this free until the function's about to return. And that includes if you have a bunch of conditionals in here, maybe you have like an early return here and there, and some loops and stuff, maybe some complicated things are going on. Doesn't matter, defer is going to say, whatever is going on there, I'm not going to call this free until all that's done. Now this doesn't work all the time. There are some cases where maybe you want to allocate the memory and then you want to return it from the function and you don't want to free it yet. You want to have somebody else in the program free it. In that case, defer is not going to be that helpful. But the point is that this can help you be much less likely to have a use after free or much less likely to have a double free. There's a whole category of things where if you just write it in this case, in this style, you're never going to write free manually. You're never going to potentially do a use after free because defer is going to make sure that you're using it before it goes out of scope. You're freeing it after it goes out of scope, and so it's not a possibility that you would have a use after free there. So this is not bulletproof, but it does help you out a lot in terms of avoiding these particular categories of memory unsafety. Now, part of the reason that Rust has a really good reputation for memory safety is that it has sort of even stronger guarantees around this stuff. Now, definitely not going to get into how Rust does this in the type system because I don't have another 6 hours to talk about it, but suffice it to say that what Rust will do is, at the end of the day, automatically make sure that this array is going to get freed whenever you're done with it, much like it would in a garbage collected language, except without running a garbage collector. Instead, it's going to do it by tracking certain things in the type system and figuring out exactly where it needs to insert certain calls to making it get deallocated only once and at exactly the right earliest time when you possibly could. So in Rust, when you're using the system, you cannot have a use after free and you cannot have a double free. Those categories of memory unsafety, much like the buffer overrun we talked about earlier, are just not things that you have to worry about in Rust. With a little bit of an asterisk, which is unless you use the unsafe keyword, in which case you can totally get all these unsafety things. But that's kind of the point of the unsafe keyword, is that the idea is to sort of minimize the amount of code that you need to think about and need to check for potential memory unsafety in Rust. It's not that you can't do it, because if Rust said there's no memory unsafety allowed whatsoever, then it couldn't meet its goal of sort of maximally using your hardware. There would have to be some performance ceiling and saying, like, bounce checks, for example, do have a runtime cost. So if they wanted to say, like, we guarantee memory safety 100% across the entire language, no questions asked, then there would be certain things you just couldn't do in Rust that you could do in like a Zig or a C that would improve your performance. Okay. So a comment that I saw, not just on this blog post, but I've just seen this like around the internet, like a pretty common thing, is people say, I don't understand why, in this day and age, anyone would use a memory unsafe language. Well, as someone who's using a memory unsafe language, I understand. But let me explain briefly what this term memory unsafe language means, because it's a little bit different from the memory unsafety that we've been talking about. So here I'm going to talk about some different sort of languages in terms of their potential sources of memory unsafety in both your application code, like what you're writing, and then also your dependencies. So I think a really easy example to compare these is looking at old school JavaScript. I'm talking about JavaScript from the 1990s, which is why I'm using their old school logo that it was back then, before they got the yellow one. This is back before WebAssembly, which kind of muddies the waters here a little bit, and also before Node.js existed. So this is when JavaScript was only running in the browser and did not have WebAssembly. I'm going to compare that version of JavaScript to Node.js. So when we're talking about memory unsafety, when it comes to application code, like if you're writing .js files in the browser back in the day, there was no possibility of memory unsafety. And this was a selling point of JavaScript in the browser, was that there were other things like ActiveX and Flash, which could have these like memory vulnerabilities and could crash the process and stuff like that and do all sorts of bad things. But JavaScript didn't. It was really, really locked down. There was no possibility of memory unsafety in the whole language, no matter what code you put in that .js file. Now, in contrast, Node.js introduced FFI, which is a foreign function interface. So in Node.js, you can actually call C, which you could not do in the browser JavaScript. And this is a source of memory unsafety, because as we've seen, C is full of memory unsafety. So this means that if you're writing your Node.js code and you use that FFI, like you do bring in like some C code, like a C library, now you have the potential for memory unsafety in your Node.js app. And this is not a possibility in the old browser-based JavaScript. But what about your dependencies? So here we have to get into a little bit of okay, it kind of depends on how you define it, because if you're talking about dependencies, it's like, well, JavaScript runs in a virtual machine, and the virtual machine can have bugs. It is true that if there's a bug in the implementation of the virtual machine, then your JavaScript code could exhibit memory unsafety. That could totally happen. And then you could also say, well, the operating system could have a bug, and that could cause memory unsafety. Okay, fair enough. So let's just agree that there is some constant number of dependencies that could have memory unsafety for JavaScript that starts at the VM and goes down. Those are potential sources of memory unsafety, as they are in absolutely every program, but it's not something that varies by how many dependencies you have. When you're writing old school browser-based JavaScript, it does not matter how many .js files you're importing. None of them are going to introduce memory unsafety into your program. Not true with Node.js. Node.js, every single dependency you have potentially could introduce memory unsafety to your program. And as we've seen before, unfortunately, one of the really nasty things about memory unsafety bugs is that they can affect other parts of your program. In fact, they can impact any part of your program. All of your entire process is using the same memory space. So if you have something with memory unsafety in one of your dependencies and it overwrites one of your bytes to turn a 0 into a non-zero, and now you have this string overrun, that can happen anywhere. And it can happen across any amount of code boundaries that you set up in terms of modules and anything else. So unfortunately, the fact that Node.js introduced this FFI means that you now have to worry about memory unsafety, not only in your application code, but also in every single dependency that you import. That's a trade-off for getting to access C code. Now, there's a whole bunch of languages that do this. Node.js is far from alone in this way. So Python, Clojure, Ruby, Haskell, these are just examples. Like lots of languages do this. They have, by default, they are memory safe, but then they have an FFI that allows you to access a memory unsafe language, and that includes in all their dependencies. There's another category of languages that kind of take it a step further. So in this case, I'm going to give the examples of Java, C#, Scala, Swift, and Go. And these are languages that have not only FFI, but also they have a concept of unsafe. So there's a first-class way in the language to write memory unsafe code. So for example, in Java, it's sun.misc.unsafe. There's just a package. I can just do memory unsafe things directly in Java code. I don't even need to use FFI and get C into the equation. which means that I need to now sort of expand my space of things that I have to consider as potential memory unsafety sources. So it's not just that I have to say, oh, am I using CFFI? Do I have .c files or C libraries in my dependencies? No, in these languages, I also need to go and audit, well, do I have sun.misc.unsafe anywhere in my code? Because if so, or any of my dependencies for that matter, if so, those are potential sources of memory unsafety, and I probably want to be more careful when reviewing code that involves those things, for example. And then finally, we have the last category of languages like assembly, C, C++, Objective-C, and these are languages where they basically, anything could potentially be unsafe. They have first class pointers and addresses, and unlike in the previous category of languages, these are not sort of off in a corner and really culturally discouraged their use. It's these are just used all over the place, and people can just use them as much as they want, and that also includes every dependency. Okay, if you're curious, by the way, Rock is actually the second language that's in this top category, where we also have, we don't have an arbitrary FFI that can infect every dependency. There's basically exactly one of your dependencies that you kind of build everything else on. We call it the platform. This is not a talk about Rock, so I'm not going to get into the details there, but that was an intentional design decision as part of trying to minimize the amount of stuff that you need to worry about in terms of memory unsafety to sort of, as minimal as possible. Okay, so I'm going to draw this box here. Called memory safe languages. So this is when people say memory safe languages, this is what they're talking about. This is where that term comes from. Now you can see that there's some nuance here. It's not like you have memory safety guaranteed 100% in any of these languages, except for arguably JavaScript and Rock. But even then, JavaScript's running in a virtual machine that can have memory safety bugs that potentially can be exploited through .js code. And Rock does run on a platform. So everywhere you look, there is some potential source of memory safety. It's really just, memory unsafety. It's really just a question of how big is the surface area? How much, what parts of the language in your code base do you need to consider as potentially memory unsafe and be concerned about versus what parts you're okay, yeah, as long as I've audited those and I'm really confident those aren't doing anything bad, the rest of my code base that's built on those, I can kind of assume is fine. And this really is kind of the big pitch of Rust, and that why Rust goes in this box is that it's the same thing with Rust. As long as you've really carefully checked out the few parts of the Rust code base that are using the unsafe keyword and things like that, and FFI, because Rust can do FFI as well, then you don't have to worry about the rest of it because the guarantees of the language sort of protect you. And that's definitely a valuable thing. And Zig, of course, goes in this other box where it's much like C and C++. It doesn't have this sort of small subset that's guaranteed to be safe, but rather it has tools that help you improve your ability to detect and deal with memory safety. And this is an important distinction, which we'll talk about in a second. So yeah, basically, I think it's important to note, whenever I hear someone say this, the first thing I think is yeah, okay, but memory safe language is not exactly the same thing as memory unsafety cannot happen here. If it were, nobody would use Rust because it wouldn't be able to reach that maximum performance ceiling. And it's also not true at the same in the same line as memory unsafe language doesn't mean that everything will definitely explode all the time. We all use Postgres, the database, we all use operating systems. All these things, they do have vulnerabilities from time to time, for sure, but they're not just constantly blowing up due to memory unsafety bugs and are unusable. I consider Postgres and SQLite to be some of the most reliable code bases I've used, overall, even though they do occasionally have memory safety problems and bugs reported. So really, this term memory unsafe language is about where potential memory unsafety can be found. That's the critical distinction within the language. So why would somebody choose to use a memory unsafe language? Well, one reason is what we ran into in Rock. If we can't have memory safety in this code, this built-in use case, we're just going to be using the unsafe keyword everywhere in Rust, and we just can't avoid it because that's the thing that we're building. If we want to build it in this way, we have no choice. Then, yeah, why not optimize for other things than memory safety? We can't have it anyway, so why bother? There's no, in this particular use case, there's really no benefit to having a borrow checker if we're just going to have to circumvent its guarantees anyway with unsafe. Similarly, you can have the opposite end of the spectrum where you're look, we're not going to have memory unsafety anyway because, I'm going to use the example of Tiger Beetle, which is a database written in Zig, and lots of cool talks about that. But this is an unusual database in that it never deallocates anything. So use after free bugs, not a thing. Double free bugs, not a thing. And also, as we saw, Zig has bounds checks on slices, so they don't necessarily need to worry about any of the big three that we talked about. Use after free and double free don't come up if you never deallocate, and if they're using Zig's slices and keeping those checks on, you don't have to worry about buffer overruns either. So at that point, what's the concern? What are the sources of memory unsafety remaining for Tiger Beetle if they're in this situation? So whereas in our case, we're like, yeah, we have memory unsafety kind of no matter what that we have to worry about. In Tiger Beetle's case, it's like, well, we kind of don't have to worry about memory unsafety no matter what. So yeah, why not use Zig if we like the ergonomics better? So I mentioned earlier there's this really important question of, okay, let's say I'm in the memory unsafe world. What help do I get from the language to help me avoid it and to prevent memory unsafety bugs? So we had this example of like, what if I have the buffer overrun, and we sort of saw that like, okay, yes, C and C++ don't really give me any help here. They just silently overwrite whatever's in that memory, which can lead to buffer overruns. Rust will give me an index out of bounds. Zig can give me an index out of bounds. Bounds checks are only one example of how a language can help us with these things. There's, for use after freeze and double freeze especially, there's all sorts of different tools that languages can help us with. So the drop trait in Rust is a good example of this. The defer keyword in Zig that we talked about earlier. C++ has a thing called RAII that can help with this. Objective-C and Swift and other languages have automatic reference counting. The list goes on. Tracing garbage collection. Zig has these really cool testing allocators, address sanitizer, UB sanitizer, Miri in non-FFI Rust. There's just lots of different tools that we get from different languages, and these all have different trade-offs. And at the end of the day, that's the thing that I've learned, like from if there's one thing that you take away from all of this is memory safety is not all or nothing. Like Rust's borrow checker is a useful tool. Rust's unsafe is a useful tool. Zig's defer is a useful tool. Zig's testing allocator is a useful tool. And all of these things have trade-offs. Sometimes you might say, I want really strong guarantees. I want what Rust gives me. Other times you might say, I don't need those strong guarantees. Or there's other trade-offs that might lead you to choose Zig, even being fully aware of the trade-offs of all of these things. Okay, so I asked this question earlier of why not C? Like we were talking about, we tried Rust for our built-ins. It didn't go well, and we said, okay, why not C? But when we learned a little bit more about Zig, we were kind of like, if Zig is an option, well, there's lots of reasons why not C. Like, for example, C compared to Zig is more prone to memory unsafety. Like, it doesn't have Zig's defer to help us out with that. It has more gotchas and foot guns from being several decades older than Zig, like silent conversions and stuff that Zig just doesn't do. Zig has you do like explicit casts for things. C has less ergonomics features, doesn't have this really nice comp time feature that Zig has. And also, what I found is that the Zig community is really helpful and beginner friendly, whereas the C community is so old that it's just doesn't value like beginners to the same degree that I've experienced in Zig. I should also mention that Zig's tooling has been really, really nice, not just on this project, but based on my experiences in this, I actually learned about this and ended up using it at work. So Zig CC makes cross-compiling C code really easy. It's basically like that's a way you can get some subset of Zig's toolchain features in a C compiler. So Zig actually ships with like a professional C compiler called Clang, and then it basically wraps that up in a really nice toolchain for doing things like cross-compilation. So at work, we use this for Node.js and Rock interop. So basically, at work, we have this really big TypeScript backend that runs on Node.js that's been around for a long time. And the goal is to migrate it to Rock in order to get a bunch of benefits that, again, are out of scope for this talk. And what we're using is Zig to cross-compile that. So we do a lot of like AWS Lambda stuff. And basically, I want to be able to build on my machine and output a Rock binary for the target that we're going to deploy it to, which is like Linux, Intel versus like my Mac is like an ARM machine, and Zig CC has been really helpful for doing that. And I only would have found out about that because we ended up considering it for Rock's compiler. By the way, if you're interested in working at a company that's doing cool stuff like this, check out vendor.com/careers because we all have all sorts of nice positions open. Cool. So. We talked earlier about how sort of the motivation for all this was having these manual LLVM calls that were super verbose and wanting to just sort of get higher level language so we didn't have to write all this for these built-ins. We talked about how some languages can compile to LLVM bitcode, which includes C, C++, Zig, and Rust, and so it can get us this like much more concise thing. Now, when we ended up using Zig for this use case, basically the way that we were combining Zig and Rust is exactly what is on this slide, which is to say compiling our built-ins to LLVM bitcode, which is actually like a .bc file, and then we have the Rust compiler sort of ingests that, sort of slurps it in, and then the Rust compiler mixes the output of that Zig compilation to sort of blends it in with the LLVM that we're generating on the fly in the Rock compiler, and then sort of outputs the same stuff. So it's as if we had just written all of those things at once. Now, but this is not like Zig and Rust sort of calling each other directly, but rather Zig is used at build time, and then Rust is exclusively used at runtime. That's how we've done it. And I talked about how, like, our first choice of Rust didn't work out for various reasons, and then that's sort of how we ended up with Rust and Zig together, using Zig at build time to generate these bitcode files and then importing them into Rust for use at runtime. But there are other ways that you could use Rust and Zig together, such as calling between them. So both of these languages can compile to C-compatible binary libraries, and also both of these languages can import and call C-compatible binary libraries. So you can use that intermediate format as a very straightforward way to build some Rust code into an intermediate library and call it from your Zig code. Or if you've got a big Rust code base, maybe you want to introduce some Zig into it, you can do the same thing. Compile your Zig code to a C-compatible binary library and then import it from your Rust code. And basically, this is the same thing as using any C library in terms of overhead and also how you do it. Like libssl is a very famous library that's used in a lot of projects. It's the same thing, except you're building your own. You wouldn't call it libssl. You would call it, lib whatever I'm doing, probably. But this is a way that you can combine the two at runtime rather than at build time like we have in our project. Worth noting that if you're going to do this, that you're going to end up needing to come up with some way to share type definitions between the two. So either you're going to have to sort of duplicate code and write like, okay, here's the type on the Rust side written in Rust code, and then here's the type on the Zig side written in Zig code, or else use code generation to generate one or the other. So this sort of leads to the question that, like, knowing that we could do this, we could do like compiling them both to binary C libraries. Why didn't we? Like, why don't we consider using Zig and Rock's compiler alongside the Rust code there in some cases where we might think that Zig is a better fit? Well, actually, we did talk about this. Honestly, for me personally, the main appeal of doing this is compile times. I really like a lot of things about Rust, but compile times is one of the things that I don't like. Zig has done a really good job of speeding up the compiler. Probably this is because Zig has a simpler compiler, but also it's because Andrew Kelly, who created it, has spent a ton of time optimizing it. He gave a really cool talk a few years ago at Handmade Seattle about how all the different techniques that he used to speed up Zig's compiler. And I have not seen those same kinds of optimization land in Rust's compiler. But this would be something that I would really appreciate, especially when there's parts of the code base that we iterate on very often. We're always feeling the pain of those compile times. Also, Zig's allocators are sort of a natural fit for how we like to structure the compiler. Without getting into too much detail, this is kind of the idea that you might want different memory allocation strategies in different parts of your code base, and arena allocation is one that we use as much as we can in the Rock compiler. This is not as ergonomic in Rust as I would say it is in Zig. And finally, there are definitely some parts of our code base that could be simplified if they were written in Zig instead of Rust. And in some cases, we would have to give up some significant guarantees for that. But those are the cases where just the nature of what we're doing means that we really wouldn't be giving up that much in terms of guarantees, or at least I don't think so. Having said that, it's also the case that we already have 300,000 lines of Rust code, and introducing the two would complicate the build even more than it already is. We've got a lot of stuff going on with these like built-ins and bitcode files and whatnot. And so like having to do like shared type definitions across the two, especially if we're generating that, there's a significant overhead to doing that, and we didn't think that that was necessarily worth it in our case. Not to mention, I've talked about how unsafe is kind of this like thing that turns off certain guarantees in Rust, but it is very nice, not just for internally, like for our own code base, at sort of isolating the parts of the code base that we need to worry the most about and be the most careful with, but it's especially nice for new contributors because we have a lot of people contributing to the Rock compiler where this is the first time they've used Rust. Maybe this is the first time they've ever worked on a compiler. Both of those things were true to me when I was starting the compiler. But now that we have like 300,000 lines of code and like a bunch of contributors, it's really nice when somebody's making their first contribution to the project to be able to review that and say, oh, they didn't use unsafe at all, so I don't need to worry about auditing anything extra carefully. Or they only use it in this one place, so let me just really carefully check that one place. Otherwise, we can sort of have a lower bar of how carefully we need to check these things, which reduces the amount of time we need to spend checking new contributions, which is really nice. So overall, we did consider it, we did talk about it, but it just seemed like for that part of the project, it just didn't seem like a nice fit. So finally, I want to talk about very briefly, why else might someone else want to mix Rust and Zig? Because depending on what situation you're in, what project you're working on, you might find, actually, I think this does make sense for me, and I'd never really considered it before. That's certainly something that's happened to me a lot in my career. Is I look back and I'm like, I really wish that I realized that X was an option back then. I didn't even consider it; it wasn't even on my radar. And if I had known about it, maybe that project could have gone better. So I'm just going to sort of speculate here, some ideas for why you might consider mixing Rust and Zig. I'm not saying everyone should run out and do it. Probably it's correct that a small minority of projects should be doing it. But I think you should at least be thinking about it because you never know when opportunities like this are going to come up that actually might make sense for you. So let's say you had, for example, like a large code base with lots of mandatory unsafe code like we do. So I'd imagine, like, I've never worked on an operating system, but I could imagine like an OS kernel would have a lot of stuff like that for device drivers and things. Then maybe you also have something, a code base where you have lots of tricky lifetimes to get right, where things are getting passed around a lot and it's tricky to remember like when things need to get allocated and deallocated. Rust could help with that. But maybe you want access to the Zig toolchain, but also you want access to the Rust crates ecosystem. Maybe somebody's implemented something really nice in like a Rust crate. Rust ecosystem's, at least today, much bigger than the Zig ecosystem. That might be another reason you might want to mix those. Or maybe you want certain marquee features that each language has, like Rust's concurrency checking via the borrow checker, but you also want access to Zig's comp time. Maybe those would be useful in different parts of your code base. Maybe that could be also a reason that you might want to consider mixing the two. At any rate, whatever the reason, whatever your combination of use cases are, I hope that over the course of this, you've found something to take away from our experiences using Rust and Zig together. Thanks very much.